Well, I have great pleasure in welcoming all of you to this NxU University guest lecture series. Very pleased to welcome. We have a very eminent theorist and physicist among us, Professor Shiraz Minwalla. Just a quick background about Shiraz. He is a faculty member in the Department of Theoretical Physics in the Tata Institute of Fundamental Research, TIFR. Prior to this, he was a Harvard Junior Fellow, and he also taught as an assistant professor at the Harvard University. Shiraz graduated, actually, if I am not wrong, Shiraz, at the top of your class. So he was the President's Gold Medalist at IIT Kanpur, the Indian Institute of Technology. He's too modest to probably sort of admit that, but anyway. And he earned his PhD from Princeton University. He actually is the recipient of India's highest science award, awarded for physics, called the Bhatnagar Award, the Shanti Swarup Bhatnagar Award as such, in the physical sciences category. I will not really sort of take too much time because his number of award list is probably endless, but the most prominent one, which he was very recently awarded, was called the 2014 New Horizons Award as well, in physics. The prize actually has been dubbed as the 21st Century Nobel by the media. So anyway, again, Shiraz, welcome. But before I start off, I just wanted to address one question which has been asked by a lot of you, because we opened it out for the entire NxU University members and our clients. And everyone asked us as to why a digital marketing agency is inviting an eminent physicist as such. So I think that was always a constant challenge. So my response to everyone and anyone who's probably going to see this video is I somehow believe knowledge is, we live in a knowledge economy. And I mean, every one of us is touched in some way or the other, or will be, by the work which Shiraz and his team are doing. These are some fundamental things which really impacts and influences and applies to all of us. And more than anything else, I mean, it's almost like experts and scientists like Shiraz who really inspire us every day and really prompt us to think beyond. Because one of the things that we have consciously tried to do at NxU University is share knowledge and try to disseminate knowledge everywhere. And from that perspective, I don't think knowledge should be compartmentalized, or knowledge should be isolated in different segments. So purely from the inspiration perspective as well as information perspective, having someone like Professor Minwalla direct and address some of the questions, we felt would be very valuable. Especially it goes very much in line with the entire value system of NxU and the NxU University as such. So what I'll try to do in this session is, we have a bunch of questions for you, Shiraz, and that has been put together by our team. And we had requested some of our clients also to ask any questions. So I'll first narrate or relay our questions as such, and then I'll mention the specific client's name and their question as well. So why don't we get started? And if you can tell us a little bit more about your area of work, and honestly speaking, how does it really influence, impact, or touch all of us?
Okay. I work on a theory called string theory. String theory is an attempt to go to the next level in building the fundamental theory of physics of the universe. So what does that mean? Physics is an attempt to get a mathematical description and a mathematical set of rules that can adequately predict the future from the past. So a mathematical description of the universe and a predictive description. And it's been amazingly successful so far. If you look at the progress that's been made over the last 300 or 400 years, it's totally remarkable. Perhaps two pillars of this remarkable success are the standard model of particle physics, which is a theory which which lists the basic constituents of matter, the basic things that make up everything we see around us, and gives you mathematical rules for how these things interact with each other. This theory is based on a formalism called quantum field theory, and is very importantly is quantum mechanical. based on the formalism of quantum mechanics, of probabilities and amplitudes and uncertainty that was developed about 100 years ago. This is one pillar of our knowledge of the fundamental structure of the real world. Now there's another pillar, discovered, created around the same time by Einstein, largely by Einstein and friends. The second pillar is the pillar of the general theory of relativity. This describes the nature of space and time. You know, it had previous to Einstein, it had been supposed that space and time was some sort of passive stage on which dynamics happens. You know, Newton has a very, very eloquent description of this. Time, unchanging time, something like that. Okay, Einstein realized that was not the case. Space and time, the geometry of space and time is as dynamical as anything else. And the dynamics of this, the geometry of space and time, gives rise to the force of gravity. So Einstein and friends came up with this very beautiful theory. Very beautiful theory. In fact, in my opinion, the most beautiful theory ever written down by human beings of the structure of space and time. But this theory was a classical theory. Okay? So it was a classical theory, which means that it's written in the language of differential equations. There's written in the language of certainty. There's a particular geometry which you can know for sure. So now we've got these two different pillars, and they're both vastly successful in their own areas of application. The framework of quantum mechanics and quantum field theory, standard model of particle physics, gives a very accurate description of experiments you perform at very high energies, very short distance scales. For instance, the experiments that are performed at the LHC in CERN, like the ones that discover the Higgs boson. Okay, it's a beautifully accurate description of that. On the other hand, Einstein's theory of general relativity gives a fantastically accurate, apparently, description of the universe at large scales. Well, the Earth going around the Sun, deviations from Newton's laws there, satellites, but much more interestingly, the dynamics of the universe as a whole. The universe evolving and so on. However, these two theories are based on different ideas. One is quantum, the other is classical. And it's a more or less theorem that it's impossible, mathematically inconsistent, for part of the universe to be quantum and the other part to be classical. Okay? So while these two theories are very successful in their own domains, we know that we are not true. Because mathematical consistency of the whole requires that Einstein's theory also be a quantum theory. So quantum mechanics is sort of like a jealous theory. It won't tolerate anything else. Just consistently, just for consistency. Okay, so in order to complete our description of the universe, we need a way of getting a quantum theory of gravity. And string theory is an attempt to make a quantum version of Einstein's theory of gravity. Now, you asked about applications. So there are two kinds of applications you could have in mind. The first kind is like the application in your cellular phone, meaning an application of economic relevance to, or practical relevance to human beings. I cannot foresee an application of that sort, over the 10 or 50 year time scale of the kind of thing we do. Though I have to say that the people who invented quantum mechanics probably could not foresee applications as well, and yet semiconductors would have been possible without quantum mechanics or computers. Okay, so it's sometimes hard to know what the applications will be till you find the theory. But having said that, it sounds unlikely that there will be immediate practical applications. However, if by application you include application to intellectual areas of activity, there are two kinds of applications of string theory that both sound very exciting. One is potential, the second is being realized. The potential application, once we understand the question well, is the following. You see, the reason we've been able to get two theories that look like they're based on different ideas, both to agree very well with experiment, is that the region, the place where quantum effects and gravity would be experimentally important, are very extreme places. The places where you've got very, very high energies or very, very high densities happening. It's very hard to arrange these places in a lab. Okay, if you wanted to do that with some sort of LHC type experiment, you'd have to make it much bigger and much faster. However, there are places in the universe that automatically had such conditions. The center of black holes is one of them. Okay? But perhaps most interestingly, the beginning of the universe. When the universe began, it was so hot and dense and high energy that gravity, which was clearly an important force at that point, was also, we believe, quantum mechanical. So in order to address a question that human beings have asked since they were able to ask questions, let's say 100,000 years ago, which is, where did this all come from? Where is it going to? We need a quantum theory of gravity. Okay? So if you count that as an application, this is likely to be the most substantial intellectual application of the quantum theory of gravity in the end. Without having a quantum theory of gravity, you cannot sensibly address questions of the very early universe.
Magnitude almost. You're talking about the early universe. Can you tell us a little bit more about as to what is the genesis of the universe? I mean, how was the universe created, let us say?
Okay, I'll tell you what we know and what we speculate. Okay, well, firstly, how do we know what we know? If you look at the universe, all we have access to in experiments is how the universe is now. We cannot go back in time and see how it was before. So when we look at the universe, what we see is the following. We see that the universe is composed of a very large number of galaxies. Okay? And these galaxies are moving away from us. The speed at which they're moving away from us, to first approximation, is proportional to the distance of the galaxies away from us. Okay? Now, if you think about that for a minute, that makes it sound like the universe started with an explosion. Because suppose there was an explosion in which things were let out at all speeds. The thing that was shot out twice as fast would at any given time go twice as far from the center as the thing that was shot out half as fast. And that's what we're seeing, more or less, to first approximation. Okay. It also, you might think, makes it sound like we're in a very special place, because if we see things go out, it sounds like the explosion happened where we were. But actually, if you look at the mathematics of what's going on a little more carefully, you see that the universe is very, very interesting kind of thing. It's sort of like a balloon. If you blow a balloon out, the balloon is a perfect sphere. At any point on the balloon, it would look as if the nearby points are moving away at a speed that's proportional to the distance.
Interesting.
But no point is special. Every point would feel, oh, we were at the center of the explosion. But they were all were, because at the explosion, when the balloon was zero size, everyone was at the center. Okay, so our universe is believed to be like that. It's isotropic and homogeneous, in other words. We'll go with this one. Okay, so what we see is this expansion outwards. Now we have to understand how it started. We run the movie backwards. Questions: how do you run the movie backwards? You can do some crude extrapolations just with the speed, but that's not good enough. That's how you run it backwards is by the equations of physics. You see, the equations of physics are those kind of equations. If you know what's happening now, it can both predict the future as well as the past. The equations that are relevant to us now are the equations of Einstein's theory of relativity. Okay, so these equations allow you to run the movie backwards. And when we do that, we see that the universe started out very small, hot, and dense. Okay? How small? I'll come to that in a minute. But anyway, this is beyond serious dispute. Okay. But that's when things start getting really interesting. What then? And then we enter the realm of almost speculation. I say almost speculation because there was an experiment that some of you may have heard of about a month ago, an experiment called BICEP2, whose results are confirmed, then what I'm now going to tell you is not speculation. It's true. Okay. So, I'm going to tell you something that is speculation now, but will not be in November, if confirmed. Okay. And this is you see, this thing started very small and hot and dense. How small? Well, if the results of BICEP2 are correct, about 10 to the power minus 30 centimeters. Okay? What happened before that? Very interesting. You see, what happened before that was this, that the universe started, that the universe was in a phase which was very rapid, where space-time was very rapidly accelerating, expanding at a very rapidly accelerated rate. But it was a very boring universe, a universe that was homogeneous. You know, the universe we see around us, a galaxy here, empty space there, it's far from exactly homogeneous at small scales. But that universe, if this theory is correct, and if we get confirmation soon, was where space and time was expanding very fast, but every point in space and time was almost identical to every other. Nothing, vanilla universe, nothing happening. Okay. Now, quantum mechanics doesn't quite allow that. You see, when I say everything, let's say you've got a field, some field that's just constant in space, that's a classical idea. In quantum mechanics, there are always uncertainties. So when I say that it was homogeneous, I mean approximately. Modulo small quantum uncertainties. Now, according to this theory, what started happening was a certain field, it doesn't matter exactly what, started rolling down a potential, stayed at the top of a potential for a long time, and the universe expanded. And then rolled down that, and then sloshed around a little bit. What they said, reheating the universe, and this sloshing around created what's called the Big Bang, the whoosh. Okay? At that point, the universe was 10 to the power minus 30 or 32, and it went shoo. Okay? Interestingly enough, according to this idea, these small quantum fluctuations that are inevitable, okay, in the subsequent evolution of the universe, got frozen into classical fluctuations. Still, to start with, very small. But you know, the force of gravity is a force that enhances instabilities. Because we've got more stuff here than there. This stuff attracts more than here. So still more will go into it. Okay? So inhomogeneities are unstable in gravity. And these inhomogeneities grew and gave rise to the inhomogeneities we see in our universe, including galaxies, and eventually stars and planets and us. So this idea is correct, and as I say, we'll get confirmations, hopefully soon, or this confirmation. But if this idea is correct, it's quite incredible. Because for the first time in the history of physics, we will have a theory not just of the dynamics of physics, but of the initial conditions. You know, the universe, physics up to very recently has addressed itself to the question, what are the laws of evolution? Give me an initial state and I'll tell you how to go to the final state. But there's no question of what is the right initial state. You know, it's whatever it is. Here we think we understand that in this situation, we understand the initial state of the universe. You can only understand it if it's very simple. And we understand it because it's extremely simple. There's just nothing happening apart from small quantum fluctuations which we can calculate. And these things give rise to everything. You know, this is a very predictive idea because it could allow you to, people try to use this idea to understand distributions of galaxies, structure formation and so on. So if it's correct, it's very predictive. Okay, and just one more, it's probably going on too long, but one more thing just before that. So you see, this thing started expanding. I said that there was this hot Big Bang. Whoosh. Before that, there was this uniform expansion with small quantum fluctuations. You can ask what before that? Yeah. Did that expansion go on forever? Yeah. Or did it start from something? And now things get interesting. You see, if the results of this experiment are correct, this expansion happened at an energy scale at which quantum gravity is important. So address questions like this is basically, completely reliably address questions like this, is basically impossible without a serious quantum theory of gravity. So we need to understand things like string theory or whatever else, right theory, better to run the clock even further backwards.
See, one of the things which I'm still perplexed with is, despite the theories that you are mentioning, is what happened before that. Yeah. So before Big Bang, what was the situation? You're sort of mentioning about the temporary sort of, let us say, homogeneous state and so on.
Yeah.
When I say homogeneous with some rufflings and fluctuations.
Yeah.
Before that, has physics been able to predict what?
Not yet, and I don't think it can seriously be expected to do so without a good quantum theory of gravity, which is still in the making.
So my other obvious question would be, I mean, if we all know about the genesis of the universe,
yes,
can you also, how strong is your theory in predicting how will it end?
The future, yes, it's actually is just the prediction of Einstein's general relativity. You see, some of you may have heard that about 10, maybe now 15 years ago, there was a surprising discovery, which got a Nobel Prize, which was that the universe, as I explained, if something starts with an explosion, how far you are is proportional to how fast you are to first approximation. But that's only to a very crude approximation. That's assuming that there are no forces between the things that are moving. But of course we know that's not true because there's the force of gravity. Force of gravity tends to pull things in. So you might have thought that actually there would be a correction to this coming from the fact that things are, that objects are actually decelerating. That is, they're not moving at constant speed, but slower and slower as time goes on. Okay? Because gravity pulls things in. And this is what, the textbooks I studied as a student expected. And to some extent, of course, it's true. But the real surprise was that when we do careful experiments, you find that at longer distance scales, this deceleration stops and becomes an acceleration. Things further away move faster. Now, you might think, how on earth can that be? Gravity is an attractive force. And how on earth that could be was actually anticipated quite remarkably by Einstein. He added a term to his equations. Actually, Einstein was worried about the following. When Einstein was doing his physics, it was obvious that the universe is a static thing. It's not. Things aren't moving. The universe is and will always be. Somehow that was in the air as an obvious philosophy. And he was very worried that his equations were not consistent with such a solution. So he was a remarkable man. After getting these equations, he applied it to the Earth moving around the Sun, Mercury moving around the Sun, then wanted to apply it to the whole universe. It's quite a leap. But he found that there were no solutions for a static universe. And then what he did was to change his equations a bit by adding a term called the cosmological constant. That when changed, would allow for a static universe. Actually, that was a stupid application, because that static universe is unstable and there are various things about it. And Einstein later withdrew that change to his equations, calling it in print his greatest blunder. Introducing this new term was my greatest blunder, because what he felt he should have done was to have the courage of convictions to make the prediction that, the universe must be dynamical, which of course was soon discovered to be. Okay, but now what we seem to realize is that actually the Einstein equations do have this additional term, but with a larger sign, larger magnitude that would make the universe static. So in fact, at large distance scales, this additional term causes the universe to accelerate. This term is called the cosmological constant. It's a very, very puzzling thing. How and why this comes about is a very puzzling thing. Okay, but that's a separate, the theory of that is a separate issue. So to address your question, if it is true that we are living in a positive cosmological constant universe, and seems experimentally overwhelmingly likely to be true, then the future of our universe is very dismal. Okay, so let me tell you about that. You see, this thing causes acceleration. So what happens when the universe accelerates is that at some point, every cluster of galaxies will move so far away from every other that you can no longer send signals from one to the other. So, at some point, quite far in the future, many tens of billions of years in the future, in our little local cluster of galaxies, somebody who's born then will have to believe the textbooks to know that there ever were other galaxies, because he can't see them. Okay? And then, so the universe gets more and more a lonely place.
Isolated, yeah.
And then energy sources will run out. The energy sources like stars there'll be maybe a few more generations, they will run out. So each galaxy will sort of cool. All life will die because of these energy sources, and the future will be steady and boring. It's like what Eliot said. This is how the world ends, not with a bang, but with a whip. Okay. However, I have to say that there are other possibilities. We have to understand if string theory suggests other possibilities. Okay. more dramatic possibilities for the, you could suddenly tunnel into another place. This is very speculative. And say, if you just accept positive cosmological constant and Einstein's equations and make no further speculations, this is what you would be left to, the conclusion you'd be left to. Which, I have to say, if you think about it, and I sometimes do think about it, it's a very depressing thought.
So essentially what you are saying is the different galaxies almost act as an overall ecosystem where everyone is sort of feeding off the other's energy in some ways, right?
Very limitedly. Yeah, that you lose contact with the other galaxies is not very important to losing your energy sources.
Okay.
But the point is that you cannot get an injection from outside. It cannot be that, let's say, two galaxies will collide with each other and that will give you some new fireworks.
Got it.
Yeah. Yeah, right.
So in terms of the work that you are doing as such, Shiraz, can you tell us a little bit more? I mean,
okay. Yeah. So what I have been doing recently has been using string theory. Okay, so string theory, I've told you about the objective of string theory, but let me tell you about the reality of it. What string theory is at the moment is an extremely impressive mathematical framework, for making quantum theories of gravity. And this framework, though it started as an attempt to make quantum theories of gravity, is a very connected framework in the sense that it makes it, in various limits, reduces to, let's say, quantum field theory, the framework for the standard model of particle physics, or other frameworks that people use in, well, studying small parts of physics. Okay? And this framework, but regarding these other small little things as part of the bigger frameworks, allows you to see connections between different branches of currently apparently well understood physics that would not otherwise have been clear. So for instance, some people, serious people, professors at Harvard, so not grandparents, hopefully, are trying to use this connection. For instance, you may have heard of high temperature superconductivity. Superconductors are wonderful things. They conduct things without resistance, but typically at very low temperatures. To be made practical, you can't run a train by cooling it down to liquid helium temperatures. However, there are these new materials, not so new anymore, 20, 30 years old, which are superconducting at liquid nitrogen temperatures, which would allow practical applications. Something that stalls this is that the theory of these high temperature superconductors is not well understood. Condensed matter physicists have been at it for 30 or 40 years without success. There's something new going on here. There are people attempting to use connections between the kind of physics that describes condensed matter physics and the kind of physics that describes gravity. So try to use the equations of gravity to try to understand high temperature superconductors. Okay? So this is irrespective of the eventual application to the beginning of the universe. Okay, so the kind of work I've been doing recently is along those lines. What we discovered maybe 5 years ago was that using the framework of string theory, that under certain conditions the equations of gravity become isomorphic to the equations of hydrodynamics, fluid dynamics, the equations that describe the flow of air or water when you're swimming, or air through an aeroplane, in a certain non-obvious way. Now this is interesting because the equations of gravity and the equations of hydrodynamics are probably the two best studied partial differential equations in physics. Each set of equations has many unsolved problems, but each set of equations has been studied to great, there's a lot of knowledge about each equation. So by connecting the two in a way that is not obvious, you learn about both sides from the other. And you end up learning that some things you thought were true about either equation was actually not true. Yeah, so that's the kind of thing I've been doing.
So essentially, does it really sort of point towards a unification of the different parts?
Yeah, right. String theory is a framework that has a huge amount of unity in it. Yeah. It takes things that you thought were totally disparate.
Yeah.
Like hydrodynamics is actually studied by engineers, right? Okay. Gravity study. Things that the same, that are not even somehow part of the same community almost, and relate to them in some non-trivial way. Yeah, so certainly that's one. That's I should mention that the key idea that has allowed this unification is called ADS-CFT correspondence, invented by the standards of the field Young, Argentinian professor at the Institute for Advanced Study, Maldacena, yeah, which was an ultimate unification. It re-expressed an ordinary quantum field theory as a theory of gravity. It's called the. Now, we still haven't really understood all the implications of this, but it's very surprising because I spent the earlier part of this talk telling you that theories of gravity, quantum theories of gravity, are not very well understood. Maldacena discovered that some quantum theories of gravity, using string theory, could be re-expressed as theories without gravity. Quantum field theories without gravity, the kind of quantum field theories that describe the structure of the nucleus. So there is a very surprising unity, whose lessons we're still trying to learn.
Okay, interesting. Well, this was very, very informative. Before I dive into some questions, I mean, if there were, let us say, two predictions that you were to make as a string theorist or a physicist, what would your two predictions be? What would really happen in your space in the next, let us say, 50 years?
It's very, very difficult to be accepted. let me just, as a cautionary tale, you know, there was this famous meeting called Solvay Conference in 1910, attended among others by Einstein, Rutherford, Bohr. Okay, this is the time when quantum mechanics was just about to happen. Okay, it had actually started happening. In fact, Rutherford had already performed the experiment that talked about the structure of the nucleus and really set off the line of thinking. But you look at the proceedings of this very famous conference. These guys are trying to predict the future. Not one of them mentions quantum mechanics. Or of course, they don't know the name. Not one of them suspects that this is where things are going to go. Okay, physicists are very bad at predicting how the field will evolve in the future. But okay, having said that, I think that there are experimentally, it's very likely that we get more and more information about cosmology. Okay, that's where much of the experimental activity is, about telling us more and more about the beginning of the universe. This is extremely interesting because it seems that this happened at energy scales at which quantum theory was, the theory of gravity was also quantum mechanical. So it's extremely interesting. From this point of view, it's also extremely interesting because the beginning of the universe is a really interesting time. We will hopefully also get more information about the structure of the universe. More information about the structure of the universe. There's this thing floating around called dark matter, which we understand very limitedly. And there's this cosmological constant, some people call it dark energy, which we also understand very limitedly. With luck, we will have better theoretical understanding of a very elementary question about why the cosmological constant is so small. You could imagine that there was a reason that it was zero, but why is it so small? The cosmological constant, I should have said, sets the scale for the size of the universe. And the ratio of the size of the universe to 10 to the power minus 20, 33 centimeters is like 10 to the power 120.
Yeah.
Okay. Whenever you see such a big number in physics, it cries out for an explanation, so some sort of explanation for why this cosmological constant is. That perhaps is a realistic, better theory of the beginning of the universe, better experiments on that, better theory of the constituents of the universe, and better understanding of the dark matter, dark energy, scale of the cosmological constant. It's perhaps realistic to hope for within the lifetime.
So talking of dark matter, actually that was one of the questions that we have from our client Peter Walter, who is the director of web marketing for Xcelligence, or Discount School Supplies, their website. What is dark matter and what would be the consequence if we find that there is no dark matter in the universe?
Yeah. So what is dark matter? Okay. I've told you that Einstein's equations can be used to run the universe backwards or forwards. And, of course, it can be done once you put in some information about what the universe consists of. So part of that information you get by just looking around. You look at the universe. You see it's got a lot of galaxies, you try to measure how many galaxies and so on. But if you put just that matter into the universe and try to run the equations, it doesn't work. Predictions are wrong. Now, there are other things that don't work. You see, if you just try to measure them, let's look at our galaxy. Try to measure every star in the galaxy, account for all the dust that we see and so on, to get an estimate of the mass of the galaxy. People do this very painstakingly. Okay. Now, there's another way of estimating the mass of the galaxy, which of course is more, it assumes some theory, but it's more direct. And that is this. Suppose you see something, let's say a star, going around our galaxy, a bit far away. Now, you can use the equations. How fast it goes around the galaxy depends on how massive our galaxy is. Just like how fast the Earth goes around the Sun depends on the mass of the Sun. Okay? So if you can measure the time period of this motion, you get a measure of the mass of the galaxy. And what people find is when they do this, they get a measure of the mass of the galaxy that is much higher than if you just count everything. Moreover, if you take something moving here and something moving here, that can give you a measure of the how much mass is between this guy and this guy. Now, when we look, it looks like empty space, so the mass between this guy and this guy should be 0. But when you measure it by these time rotations, okay, you get a non-zero answer. So this was very puzzling at the beginning, but everything that we see seems consistent with the following hypothesis: that in addition to the matter we see, there is additional matter in the universe. This matter interacts very weakly with the matter we are made up of. So the stuff streaming through your body as we speak, according to this idea, but because it doesn't interact with the stuff we're made up of, we don't care, we don't notice it. This stuff is called dark matter, and its primary impact on the universe at the moment is through its mass. You see, how different particles interact with each other through specific forces like electromagnetism, or the strong force of the weak force that make up the matter, that are important to the properties of matter as we see it, depends on their specific constituents, how they constitute it. But everything in the universe interacts through gravity. Gravity is a universal force. So this dark matter, irrespective of what else it does, it must interact gravitationally. So the idea is that this dark stuff is interacting, to first approximation, only gravitationally. Okay? This idea accounts in quantitative detail for many things, for the detailed evolution of the history of the universe, as well as these galaxy rotation curves, as well as many other things. Okay? So what is dark matter? The answer is, that we believe that only about that the matter we see is about 20% of all the matter that there is. The remaining stuff is stuff that interacts very weakly with us. But it interacts gravitationally. So this is what dark matter is. Now, the question was, what if there is no dark matter? If there's no dark matter, that's a revolution. Because as I told you, without dark matter, what we see is inconsistent with our equations. It would tell us that we don't understand physics at all. Now, this is the conclusion some people draw. There's a community of people who try to explain these changed rotational curves by modifying Newtonian gravity. A theory called MOND. They try to do something similar with cosmology. Maybe, I think it's unlikely. But so if there's no dark matter, it would imply that many things we think we understand, we don't understand. But I should say one more thing about dark matter. You see, this situation where you have to postulate something without seeing it is in the end very unsatisfying, because you're never really sure. It feels a bit like a fudge. Okay? So, there is, of course, a huge experimental effort in trying to detect dark matter. It shouldn't be too difficult, depending on exactly how weakly this dark matter interacts with us. So, these experiments are very simple. What they do is to take huge amounts of water, let's say, in a tank, and surround it with detectors. The idea is, as I've said, that there's dark matter floating through everywhere, including through this huge amount of water. So even if the interactions are very weak, once in a while, one of these dark matter particles will bang against the nucleus and cause something you can measure with the detectors. So that's the way people are hoping to detect it. How well you'll be able to, whether you'll practically be able to do the detection in this way depends on the strength of the interaction. It's very weak. So, okay, that's one way. The second way, of course, is to understand what the hell this dark matter is. Now, there's this other experiment at CERN, the LHC, where they're banging things against each other, looking for new particles. So far, it has only confirmed well-understood theories of physics, standard model physics, the Higgs boson. But we strongly believe that there's something new that we haven't seen. Part of the reason we believe that is that we think there's dark matter. So if there's dark matter in the universe, you should also be able to create it by banging two things together. So that's the other attempt, to find this new particle in a laboratory, not by just looking at its streaming theory, but by creating it. And there is a chance, in answer to your earlier question, that of a grand synthesis. It could well be that dark matter experiment, 10 years will find dark matter, that an accelerator experiment will create it. And then we will have this grand synthesis, that is this new particle in particle physics will also become the new constituent of the universe. Yeah. That would be very satisfying, because we would understand it in great detail. We'd be able to characterize its properties, we know for sure it existed, and that's the hope.
So I have one last question. This has been asked by, again, our clients, Rick Emer, who's the Chief Operating Officer for That Pet Place. It's a rather long question, so I'll sort of read it out to you, Shiraz. String theory requires the addition of several dimensions beyond those we have been able to observe in the universe. The multiverse theory, as I think I understand it, seeks to explain these missing dimensions, but also implies that they are unobservable. Is this correct, or is there some way of validating the existence of other universes and their additional dimensions?
Okay, great. So firstly, I should say that we should distinguish between additional quote-unquote universes and additional dimensions. So let me just explain both of these. Let me try to address. See, it is true that in the simplest and perhaps most traditional versions of string theory, the universe that we see has 4 dimensions. There are three dimensions of space that we can walk around in. There's time, which is counted for some reason as a dimension. But it also has, depending on details, let's say 6 or 7 other curled up dimensions. This idea is not inevitable in string theory, by the way. Okay. We don't need to get into that, but if this idea is correct, this is very much part of our universe. These dimensions are not unobservable. We will one day observe them. For instance, the bicep experiment, if it's correct, tells us that these dimensions, if they exist, have to be curled up at distances smaller than 10 to the power minus 30 centimeters. Because if this very rapid acceleration happened at when these dimensions were bigger than the scale of these accelerations, these dimensions would also have expanded, and then we wouldn't have been living in 4 dimensions today, we'd have been living in 10 dimensions. So what I'm saying is that the properties of these additional dimensions have experimental consequences in our universe, and one day we will, if this is correct, we will detect them. Okay, so it's an interesting question about what these dimensions are, what their role is, and so on, but let's put that aside. But the question was, the second part of the question talked about this idea of multiverses, which I have to say is an idea that some physicists talk about seriously, but is more in the popular press than in physics discussions. And it's an idea, a very, very, very interesting idea, in which you've got some accelerating phase, some master accelerating phase, and then every once in a while, what's called a tunneling event happens that takes you from this master accelerating phase into a new sub-accelerating phase. And that our universe was one of these, that the inflation I talked about was one of the sub-accelerating phases inside this master universe. So we've got this accelerating stuff, some master accelerating stuff, which we don't easily access. Then there's some tunneling events, some part of the universe goes into some other phase. It's a little like water going to ice. water going to ice when it's not favored. But it doesn't matter. And then a new sub-acceleration starts here. But the idea is that in this master, big, huge accelerating thing, many of these little events keep popping up. But because all of these events keep popping up inside this big, huge accelerating mess, these things are basically causally separated. So these little sub-universes cannot talk to each other. That's an idea. It's a very interesting idea, but it borders on not being physics. Because if you have an idea that you cannot in principle test by communicating between these other universes, I mean, you have to wonder about whether, I mean, okay, I should say that. It is physics, but it's very, very speculative physics, even set from the point of view of a person who doesn't mind speculating. Okay, these many little baby universes could each have their own dimension, structure, and so on. Now, issues about the multiverse, as I say, are very speculative at the moment. We have to understand the theory much better in order to seriously talk about that. Issues about extra dimensions will have clear, observable physical consequences and are separate issues.
Excellent. Well, I mean, this has been great, Shiraz. Just wanted to sort of summarize, probably for some of you who may be interested. So, I mean, just discussing with you, there are 3 or 4 observations which obviously came out, not essentially on the area that you are talking to, but some of the characteristics which you very clearly express, right, or exhibit. And the first, I'm just trying to almost like extrapolate that for being a successful scientist, or let us say mathematician, or let us say string theorist, what are those essential requirements that any person needs? I mean, if there are certain students who are watching this. So, I mean, to me, what came out, one was a relentless curiosity, understandably. The second is, I mean, you almost like come across as a person who, you would rather sort of be much more comfortable with certainty and try to sort of solve towards that, right? So rather than speculation, there has to be some sort of a mathematical answer, and till that time you get to that, there is this relentless passion which drives you forward, right? Would you think that
That's absolutely right. Also, you should always be full of doubt. You know, as you say.
Questions, yes.
Question and have a certain irreverence to authority. You know, let me quote Feynman here. Feynman at some point said that one of the most difficult aspects of doing creative new science is that requires disregarding ideas that have become commonly accepted as correct. Okay, so there are many different. It's a problem of great complexity because these ideas explain many experiments, and therefore they sort of get the status of unchallengeable truths. But any real progress involves overturning old ideas, and so you have to have a little. Yeah, there are many things you have to have, but it's essential to have a certain irreverence to authority. To people who tell you, no, this is how it is because it's in this textbook. You say, okay, maybe not. I mean, not in a stupid way. Okay? Yeah. You can't do this in a stupid way, but you have to be a bit cocky.
Yeah.
Feynman was very good at that.
Well, excellent. Thank you so much, Shiraz. Pleasure. You are the first guest speaker on a very different topic other than digital advertising. Thank you very much. It was exceptionally valuable. Thanks a lot. Thank you.